Okay. Yeah. So as I was saying, the generalized Langevin equation is a rather abstract equation, and also it is very hard to visualize what this random force is all about, and yet it's not random. Uh, so the only way we will get a physical feel for it is when we are able to compute it for a model system. And if we cannot compute it for a model system, then we would never get a feel for what this quantity would look like. Okay, that is the point I want to make. Now, if you go out and scour Journal of Chemical Physics, Physical Review E, Physical Review B, um, various other condensed matter journals, and statistical physics journals, I very much doubt you will find more than 2 or 3 systems for which the random force has actually been studied. All right. So that is to say that the calculations tend to be so involved that people tend not to study these models almost. As a result, little is known. Now, that said, in 1991, I stumbled across a simple problem, which was non-trivial. And after some effort, I managed to calculate everything needed, including random force. So that is one of the very few published works on random force calculations that I'll have you guys try out. Just calculate that. I think nowadays with using AI or computer algebra, things are easier to do. Now, let's now question, why is the random force so important? When you do a physics problem, it is very important that you have a physical feel for how the quantities behave like. For example, does it fall off, according to some pattern in a given system? The question we can ask. And if that given system we have chosen is somewhat similar or mappable to some other very different system, then one can imagine that this quantity that you have calculated for one system may also be the same in the other one where it has been mapped over, right? So in physics, that's how we like to stretch our knowledge, because doing a calculation for that may be very difficult. But if you know the answer from a simpler problem or from another problem, it simply takes care of the right side of the equation here and there. And then you have to just find the memory function by getting rid of the integral somehow, or guessing the right memory function and doing the integral until it fits. It's some kind of self-consistency study. So at least you have eliminated one part of the problem, and that allows you to make a much more precise model or better level understanding of a physical system, right? So this is one of the points I want to make, and I'll come back to this point, because the stochastic approximation, while it can be very good in many systems, it can also be pretty bad in many systems. And notorious in that are studies on a variety of liquids. People assume liquids have short-term memory, so the memory function decays quickly, and therefore a delta function approximation, meaning a stochastic approximation, may be all right. People assume that. But it turns out it is not all right in many cases. And if it is not all right, then you get bad results. And then if you're trying to compare with experiments, you simply don't know what you're doing, because your quality of work falls. And there is a whole set of papers, I would say thousands of papers, that have estimated memory function incorrectly in the literature. People assume it's short-lived because that simplifies life and gets you towards Brownian. But Brownian is very special, as we shall see. If you approach it from this angle, stochasticity is very special. A lot has to happen for something to become stochastic. The argument I'm making is that nature, in general, likes to preserve memory if it can. It doesn't like to get rid of memory very quickly if that can be avoided. So that's one of the points I want to make. And then I want to move on to this transverse dynamics problem that I outlined last Thursday. So as you can see, the Hamiltonian here is simply that of an Ising model. There's nothing special about it. We all know it's a spin-up, spin-down model, nearest neighbor interaction, and it's minus j, so it's ferromagnetic, meaning that all spins pointing up or all spins pointing down will lower the energy because of that minus sign. And if this were a plus sign, if it were plus j, then up spin and down spin will lower the energy. So that will be an antiferromagnet. You could have taken an antiferromagnet. Your results actually wouldn't change much in this case, excepting for some details. But the ferro is easier. So that's the reason why we are taking this. Now, the point here is because it is ZZ, and because Ising model has only Z spins, you can trivially see that the Z spin of a site will commute with the Hamiltonian. So if the Z spin of a site commutes with the Hamiltonian, you can never have dynamics. So Ising model alone has no dynamics. Okay. Now let me add a little thing next to it. While yes, Ising model alone has no dynamics, people do Ising dynamics all the time. So what are they doing? The way they do Ising dynamics is they assume that, and it's a physically motivated argument, they assume that the spin will flip. And that spin flips are simply probabilistic events, dynamically, they're stochastic in nature. If you are at a finite temperature, screw the commutational law, temperature will require spins to flip. So therefore, thermally induced spin flips will happen. And if you can write a master equation, meaning flip probability in time on one side with some kind of interaction on the other side, or stochastic term on the other side, or some combination of the two, then that will become like a master equation that will give you some kind of probabilistic description of the spin flip process. This particular problem is called Glauber dynamics, which I had indicated earlier. Class, but it is called Glauber dynamics. And this was introduced by Roy Glauber around 1960. Journal of Mathematics. Nice paper. But it's a probabilistic event. You can see it, right?
Yes, I can see it.
So we will stay away from Glauber's work because we are looking into a quantum problem. Where did it go? Oh, here we are. Okay. Always have these adventures. So as I told you, that
it is going outside of the screen right now.
What is?
Yeah, so this slides that you have shared, they are going outside
Of your screen?
I guess you have, yeah, outside of it. I guess you have zoomed in, so you may zoom out.
Is that better?
Just now move it to the left.
Move it to the left.
Mm-hmm.
Like, I can't move it to the left really, it is centered. Hang on one sec.
I guess.
Is this better?
Yes.
Yeah, this thing is a little bonkers because I don't know why it's doing this. But anyway, now you can see, right?
Yeah.
So, so what we will do is, since we can't study normal dynamics in Ising model, we will study what is called transverse dynamics. And what is transverse dynamics? Transverse dynamics is we don't interrogate the z spin in a site, but we interrogate either the x spin or the y spin in a site, and the x or y spin would be transverse to Ising. So that's why it's called transverse dynamics. So question was asked by this gentleman here, Robin Stinchcombe, quite a well-known character from Oxford. Stinchcombe posed a question basically, what kind of systems show this transverse Ising behavior? And this is what I showed you last time, where, let me go to the next one. Can't go like that. Can you see now?
Yeah, I can see.
Okay. So these are some of the systems, as you can see, these are ferroelectrics. They're called order, disorder ferroelectrics. Order, disorder ferroelectrics are systems that can be in one state or the other. So they're effectively Ising, and they have transverse dynamics also. And there is also the second bunch of systems here that, yeah. Yeah, so ferromagnets with uniaxial anisotropy, rare earth compounds, simple Yarn-Teller systems, blah, blah, blah. All these are examples of transverse Ising model. And the reason why it matters is today, this was in 1973, but 50 years later, the interest in transverse Ising model has really come back. Why? Because it is seen.
Sorry, first one second. I got one nose.
Oh, you better go. So we'll wait a little.
Sorry.
No problem, no problem. Huh. Tony needs to go to the bathroom. His nose is bleeding. So let me stop here and then I'll start.
His nose is bleeding.
Yeah, probably from the dryness because of the heat.
Okay.
I also have nosebleeds quite often here because it's very dry. When it gets cold, the heating units are firing, right?
Okay.
So that really dries your body up. So at home, I always have a humidifier going simultaneously. And sometimes even two humidifiers going. Otherwise, I'll also have nosebleeds and stuff.
If I remember correctly, if your nose bleeds, that means the air pressure is lower.
That is one way it can happen, because that then raises your blood pressure compared to the air pressure. So that is one reason why. So when I go to the some states which are very high up, for example, New Mexico is a mile high. The plateau in New Mexico is 1 mile high, so it's about 6,000-7,000 feet high. That's the base. Same with Colorado. The base is about 6,000-7,000 feet high in Colorado, the plateau itself. So I have nosebleeds very commonly. But here the nosebleed is because of dryness. Basically the nose dries up, the skin cracks up, and from that it happens. We tend to forget how important our nose is because it is extremely sensitive, right? It's super sensitive to all kinds of molecules and humidity and this and that. Better? That's all right. He was asking why, he was getting a little worried. So I was saying that nosebleed is very common here in winter time.
In the winter, yeah,
Yeah.
it's so dry.
Yeah, very dry. So it's a common problem. Okay, so anyway, so the point is that there are many, many systems where you can find transverse Ising model. And the point I was making is that after this, people got interested in being able to do small system-based computing, this quote-unquote quantum computing, the small system-based devices that can do logical operations. the interest really roared in making these small systems in the laboratory. And what else is going to give you a bona fide quantum system than a transfer? And that is basically the reason why the transversizing model has become a real darling of physicists after many, many years of being completely ignored as a problem that is for old timers. Okay. Now, and there are physicists who have spent all their lives studying these systems rigorously. There was a guy called John Stevenson. John Stevenson got his PhD in Oxford, not with Stinchcombe, not in Oxford, in London, but with Michael Fisher, when Fisher used to be in London early on. And after that, Stephenson ended up being a professor probably in the University of Edmonton or someplace in British Columbia, not British Columbia, the one to the right, Alberta, in Alberta, yeah, University of Alberta. And John Stephenson, all his life, he wrote like about 100 papers. All the papers were on the transversizing. That's all he did. So it used to be that important. Anyway, it's a model that one is well advised to pay attention to. And here is a newer paper which tells you quantum simulations of the transversizing model, experimental work with trapped ions. This guy, this fellow, Rajibul Islam from Waterloo, is one of the young, talented experimentalists there. He's an Indian-born physicist here. Anyway, but there are very good people. They did the study. It came out relatively recently, 2011. Anyway, so that's just for telling you about this. It's volume 13 of New Journal of Physics, October 2011. You can look it up if you're interested. And here is another study, dynamical quantum phase transitions. So quantum phase transitions are also one of the things that these transversizing models show. And for that reason, it's also of interest from a quantum phase transition standpoint. You know, quantum phase transitions came around in the last 20 years or so, primarily introduced by Subir Sachdev when he used to be at Yale. And Subir then moved to Harvard. And so the quantum phase transition effort multiplied after he moved to Harvard. But a transversizing model has also been their bread and butter model. So there is a lot of interest in this model. And I wanted to mention that because if you don't know it, then you miss one of the big things that has caught people's attention in the transversizing models, the quantum applications. So we'll go back to the formalism. And we will now try to do some simple calculations of what we will call transverse dynamics. Okay. So this transverse dynamics business is a little funny, right? It's not normal dynamics. We'll call it transverse dynamics. Why? Transverse dynamics because Ising model can only have transverse dynamics. Ising model can't have normal dynamics of SZ spins. So that means the dynamical variable would be an Sxk or an Syk. Either one is the same, gives the same physics. And in this case, we take all k. N goes to infinity, so basically it's a whole bunch of spins. And then there are two neighbors at the very least, which are the Z spins. But everybody else has been made into an X spin. The way you make into an X spin is you apply a transverse field and make this transverse field relatively short-lived, so time-dependent transverse field. And when you do that, some of the spins acquire orientations in which the Sx or Sy piece has been activated by the field, because the field only couples with that spin. So therefore, this transverse spin can be done, experimentally can be done. It's also called perpendicular uh, dynamics. Anyway, so now you can immediately calculate the scalar product of F0. And this quantity, immediately, it is pretty obvious that it's a weird quantity for an Ising model because Ising model only has ZZ spins, right? So how will you even incorporate a calculation with X spins in an Ising model? The way you do it is you assume that the transverse field is turned on, so the X spins are activated and then turned off. So the energy has already gotten into the X spin. Now the X spin has to interact with the Hamiltonian to relax. Question is, will it relax? So what to expect for us? If it relaxes, then the Hilbert space dimension should be infinite or should go to infinity, because that's the only, you see, finite Hilbert space means finite number of frequencies. That's what it means. Because if you go back to the picture of the continued fraction, where was it? Before that. Yes. Suppose I chop this continued fraction off at delta 2. The fraction is z over, actually z squared plus delta 1 z in the numerator and z on the top. Correct? So therefore there are two frequencies. One would be z equal to 0, which would correspond to an omega equal to 0, and the other would be z equal to plus minus square root of I root delta 1, right? So now you can immediately see, if you have a finite number of deltas, you'll just get a finite number of frequencies. Okay? So when d goes to infinity, then and only then will you get relaxation. Only then the system will go back to equilibrium. Otherwise, the system will not return to equilibrium. So this is a conceptually important point. So question is that in our transverse Ising system, do we actually get d going to infinity or d less than infinity? And the only way to know this is to actually calculate and check. So we'll calculate and check. And you can see this very important quantity has now come up, Sxk, Sxk Kubo product. And this quantity in general is not easy to obtain. And it has a name. It is called perpendicular susceptibility. Perpendicular susceptibility. You see, while the Ising model in 1 dimension or 2 dimension or 3 dimension in general is solvable, at least numerically solvable, partition function may not be exactly calculable in 3D, but we can still get pretty close to it. You see, partition function is not even exactly solvable if you have a transverse Ising model in 1D, unless it is at 0 temperature. Okay, so only 0 temperature transverse Ising model in 1D can be solved. And this solution emerged in 1961. And this solution is called Lieb-Schultz-Mattis theorem. Lieb-Schultz-Mattis theorem. And this was published in Analytical Physics. In 1951. Actually, Lieb, Schultz, and Mattis solved 2 problems in one go. One was the transverse Ising model. So partition function z of Ti model and z of xy model. What is xy model? Instead of writing SZI plus 1, you write SXI plus 1. plus SYI plus 1. That is called XY model. Only the X spins and the Y spins interact, not the Z spins. So at t equal to 0, this problem has been solved. That doesn't mean at higher temperatures it can be solved easily. It's not. Anyway, point I'm trying to make is perpendicular susceptibility is hard to calculate. So what we will do is we will immediately do a very simple study. We will calculate F0. F0 is already Sxk. We'll calculate F1. When you calculate F1, F1 is trivial. So F1 is F0 dot. Okay then? I don't see any blood yet. So F1 is F0 dot. And F0 dot is simply commutation of H and Fc. That we already have seen. Achha, I sent you guys the PowerPoint file, right?
Yes.
That's what I thought. So now this computation boils down to a computation of the Ising Hamiltonian, comma, this Sxk sum over k equal to 1 to n. So it is a computation which is of the form of AB comma C, right? AB comma C. So it is A, the way you do it is A, BC plus CAB. If you work it out, you will see that this is the relationship that comes. ABC plus CAB. Let me take out my notes because I don't know why this thing goes up and comes back, but yeah. Okay. So if you do this ABC plus CAB, it is pretty straightforward. It has got quite a few steps, but you immediately get this result. You get this SZK, sorry. Yeah, SZK minus 1, this is a Z, hard to see. SZK minus 1, SYK plus SYK, SCK plus 1, and I is there in both the terms. It must have the I. There is another I coming in from the Hamiltonian piece, and therefore these two I's are important. They interact and become one. Now, if you look at the structure of this F1, I want you to notice something. You have taken a spin and you have tipped it, and this excitation is now going to spread to nearest neighbors because the Hamiltonian entails nearest neighbor interactions, right? So if I get perturbed, then I interact with the two of you, then two of you would immediately get the information. That's basically like how it is. So one is on the left, one is on the right. Therefore, this is like translation invariance. So SCK minus 1 SYK, SYK is k plus 1 is a hallmark of translation invariance, right? So if you don't have two sides, if you are sitting at the edge, then one of those terms will go away. And I'll hold this thought because I'll come back to this maybe in a week or so. So SZK minus 1 SYK plus SYK SZK plus 1 is what we have for F1. You don't have a delta 1 you don't have a delta 1 yet. So now we have to go to F2. F2 would have delta 1 F0 as per our first recurrent solution. But before we go to F2, we need to obtain delta 1. And there is a little bit of a challenge there. So F1 scalar product will now have a double sum because it will have a K and an L both running from 1 to N, where K is for one term and L is for the other term. So you're multiplying, you are basically doing a susceptibility calculation which looks like this. And if you now multiply one with the other, the question is what happens? How do the K's and the L's mix? That's the question. Because now you see, you're doing a scalar product, right? So you are multiplying the F1 with a K index and then with the F1 again with an L index. So clearly now you have four terms. How will these terms interact? Actually, the interaction of these terms is not simple, so I can show you this calculation a little bit. Let me try and do this on the board. So I'll just do the multiplication here. This multiplication. I will briefly show you. So what we have is we have this F1, which we call F1 with this notation. This is going to be equal to J squared K comma L equal to 1 to N. And then it will have the following scalar product. It will have a zk minus 1 syk comma a z L minus 1 sy L. Okay, plus as zk minus 1 syk comma syl as z L plus 1. So likewise, there are two more terms plus syk as zk, so syk as zk plus 1 and then as z L minus 1 syl and then plus syk as zk plus 1 and then syl as zl plus 1. So you have to know how these terms are going to interact. That's something you know. And this interaction you can only do by actually multiplying the whole thing out, which I do in the appendix B. I show appendix B here. This appendix B I'll have to send you. It is done in some detail. Essentially multiplying it out. But as you multiply it out, what happens, you see, is that only if K and L are the same will the terms give you a non-directional result. If K and L are not the same, suppose K is L plus 1, then this K will interact with this L plus 1. So Sy and Sz multiplication will give you an I Sx with a minus, right? And the trace of I Sx is going to be 0 because Pauli spin matrices are traceless. Okay? So that is the primary reason why this thing simplifies. And once it simplifies, then you can see that this equation 32 becomes the form. Okay? Actually, you can, although, I mean, I don't really do a very extended proof in part because, you can't do that for a journal. But in my thesis, I tried to do a little bit of this proof and I realized that is not really necessary because you can actually begin to see why it becomes traceless and 0. So immediately you see that you have now this SYL term, this is a susceptibility. This is also perpendicular susceptibility, but instead of being in X, it's in Y. So they're the same. Meaning, whatever perpendicular susceptibility is the same as the other one. XX1. And here you see it's a different kind of term. You have an SYL. Then you have an SZL minus 1, SZL plus 1, SYL. It is not an easy term and I will avoid doing a direct attack on this term because that term is going to be hard to do. So delta 1 then, delta 1, which is F1 over F0, then becomes the following quantity here, in square brackets, J square over 2 times 1 plus 4. Then you have this 4 spin term, and then you have this 2 spin susceptibility, perpendicular susceptibility at the bottom. And just to simplify my life, I'll call it 1 plus 4 chi star. What is chi star? Chi star is this 4 spin quantity, scalar product, product, divided by SXL comma SXL sum over L, which is the perpendicular susceptibility. You have two chi's. One is this perpendicular susceptibility that I don't know yet, and the other is this chi star, which I don't know yet. Actually, this perpendicular susceptibility was first calculated by Michael Fisher and one of his students in 1967. So it is known, but I don't know yet here. And this chi star quantity was also calculated by somebody. No, I apologize. This chi star quantity was first calculated by me. It was not calculated by anybody else. So that's in the published work. Yes. Anyway, so let's move on to the second stage. So now F2 will be F1 dot plus delta 1 F0. Okay. So F1 dot will now become a 2 spin to 2 spin commutator. So it's like AB comma CD, right? And I can show you what this AB comma CD goes like. So AB comma CD, very easy actually. Just a little bit tedious work. This will be AC BD. If you're doing it in the right order, first to avoid sign errors, A, B, C, D plus C, A, B plus A, comma C, B, comma D times. This is your commutator for AC, comma BD. Okay. So you apply that rule over here, just like I have done. And keep in mind that if the same spin gets squared, square of a Pauli matrix is an identity matrix. So the 2 halves, 2 h bar over 2, h bar has been set to 1, so 2 halves become 1/4. Okay, so that's where the 1/4 comes from. So F1 dot, we already know, F1 dot is minus 2j square, 1/4 SXK plus SCK minus 1, SXK, SCK plus 1. That's what we have. That's what we just studied. That's what we have just calculated from here. So F2 now, F2 is the F1 dot piece, which is this piece here, plus the delta 1 F0 piece. This is delta 1 and this is the F0 piece. Okay. So now F2 becomes, you see, this 1/4 SXK term in F2 interacts with the 1 plus 4 chi star SXK term on the right, second term on the right. And because of that interaction, you will find that this 2j square over 1/4 SXK with a minus sign will cancel out the j square over 2 plus SXK. So these two terms, this first term on the right side, the SXK piece, and the second term on the right side of equation 36, SXK piece will cancel out. And you'll be left with this new F2 structure, which is 2j squared chi star SXK, which is that term, the extreme right term, minus the 3 spin term. Now you see something interesting. You see, if it were not the Ising system, remember first time we went from SXK to K minus 1 K and K plus 1 K. So the spin was still coupled to the original perturbed site, K site, but it involved K minus 1 spins and K plus 1 spins. That was in F1. F2, one would have thought, will now go to K minus 2 spins and K plus 2 spins. But that didn't happen. That would have happened if it were not an Ising mode. But this commutation is unable to invoke the K minus 1, K minus 2, K plus 2. It just invokes 3 spins together here on the right. And that is pretty weird, because what it means is the kiss of death. The kiss of death is, if you now compute F2, you get this quantity here. And so delta 2 immediately now becomes J square over 2, 1 minus 4 chi-star. This is now delta 2. Let me take you back to what delta 1 was. Delta 1 was, where did we compute delta 1? Here. Delta 1 was J square over 2, 1 plus 4 chi-star. 1 plus 4 chi-star. Now it becomes 1 minus 4 chi-star. The excitation gets localized because it's unable to spread. It cannot invoke K plus 2, K minus 2. Okay? Hamiltonian doesn't allow it. That's the problem. So how can it make a new F3? To make a new F3, it will have to involve spin operators that will be orthogonal to F1 and F2 already, F0, F1, F2. But to get to this orthogonality being satisfied, it has to bring in K plus 2, K minus 2, but it cannot. So if you now compute F3, the commutation here, basically this relatively straightforward old commutation, the new one, AB, CDE, is this formula here, which you can work out actually. Just like I did ABCD, this is ABCD, another step down. The moment you do that, you find that your F2 dot becomes basically a commutation between and 2 spin and 3 spin. So let's go to the next one. Now F2 dot becomes this guy. F2 dot becomes SZK minus 1, S by K, S by K, SZK plus 1. But we have seen this before. This is exactly the structure we had for F1. Okay. So now if you make delta 2 F1, F2 dot plus delta 2 F1 to make F3, look what happens. Your Hilbert space now closes up. Because system says, well, you cannot make any unique F3 anymore. You have already used up everybody who was allowed. Because commutation will not allow you to spread beyond this point. And this is basically the reason why I chose to do this problem. Because I could show you how Hilbert space can close up. Okay, Hilbert space doesn't usually close up, but this is a very unique problem where Hilbert space closes up. In this case, you have two neighbors, and because F3 becomes 0, Hilbert space dimension becomes 0, 1, and 2, so 3-dimensional. So Hilbert space dimension D will turn out to be Q plus 1, where Q is the coordination number of nearest neighbor. So in this system, and this was something that we were able to show on paper. The conclusion becomes that this D, the Hilbert space dimension D, is the coordination number Q, number of nearest neighbors plus 1. So in other words, if we have nearest neighbors 2, then D will be 3. Okay. If we have 3 nearest neighbors, so suppose you have a spin in a triangular line. So like this. Honeycomb access on also process. 3 neighbors. Repeat setup. So for this system, Q would be 3, and therefore dimension would be 4. And indeed, that's what one can show with great difficulty. And actually, one can do very good calculations because this particular system, Q equal to 3 Eisenhower, was solved by a gentleman. His name was Hautapel, R.L.F. Hautapel, and this was in Physical A in 1950. So I could just steal Hautapel's results and show rigorously what exactly came out of it. And then, if you go to the Ansager solution, which is for square lattice Eisenhower model, right? This is the famous solution of Ansager, where there are 4 neighbors. Then you have Q equal to 4, it becomes a 5-dimensional. So that 5 becomes 0. You can even go to a triangular lattice, which is this lattice. And you see here, this pin, there are 1, 2, 3, 4, 5, 6. In 2-dimensional, the densest lattice is triangular. So if Q equal to 6, you get a 7-dimensional space. And similarly, in 3-dimensional system, if you get a simple cubic lattice, also you'll get for a spring. So although you can't do a calculation of an Ising model in 3D, you can still show the structure of the problem. So this then becomes the problem. And therefore, it also means the following. It means that if you now do a mean field theory, mean field theory is basically a D going to infinity system, which means Q going to infinity system. So mean field theory is like this. Mean field theory would say that we have a spin here, and everybody around you, the whole system around you, is at a fixed distance. There's no real distance. So therefore, n goes to infinity, the thermodynamic limit, and so d goes to infinity. You have an infinite number of neighbors. You have an infinite dimensional Hilbert space, and what that means is that your system will relax. Okay. So only way you can make it relax is by going to infinite dimensional space. I will not do that problem, but I wanted to give you that result because it's a little involved and it's tricky. But it can be done. I'll send you the paper with the results. Anyway, so how do you do the remainder of the calculation for the Ising model, Ising chain? We already know delta 3 is 0, so therefore it becomes second order polynomial on the numerator and the third order polynomial in the denominator, which essentially means z equal to 0 will create a pole. So z equal to 0 becomes one case and 2 other cases. So you can use, for example, like the method of residues to compute inverse Laplace transforms. And in this case, for z going to 0, you get this frequency, and for z going to I square root of delta and minus I square root of delta, you get the frequencies that I have here. I'll show you in a moment what happens. But best is to use a simple method like residues to do this. By the way, inverse Laplace transforms like this equation 42 here is not easy to do, okay? In this case, it is simple because d goes to infinity. But by and large, inverse Laplace transforms may be quite complicated and unmanageable. And for this simple reason, people tend to avoid doing inverse Laplace if one can. But they're also very convenient when they're there. If they can be worked out, very convenient. I might have more to say about this later, but here it's very simple. So you can actually do an exact calculation, and you find that A0 of t becomes the zero frequency mode, delta 2 over delta. Cos 0 is 1, so therefore no time dependence. Here you have this e to the minus I root delta t, and then e to the plus I and minus I. And so you can essentially write it down as one single frequency cosine of root delta t. So this is cosine of 0, this is cosine of root delta t. So you have two frequencies in the problem. Two frequencies. Actually, the poles for the first transform, the poles would end up on being here. So this is like x and this is iy. So one would become here and one would become here. This is I root delta here and this is minus I root delta here. And they correspond to the same frequency. The same frequency produces one positive root along the imaginary axis and one negative root along the imaginary axis as shown here. And therefore, we have the structure that we have in equation 44. Now, once you know A0 of t, as we have already discussed, we know all the A's, which means we can find A1 of t by differentiating according to recurrence solution 2. And we can find A2 of t again using recurrence relation 2. So you have the full story here so far, but there is more. That is the reason why I'm doing this problem. There is more. So we have done the whole story. We know F0, F1, F2, we know A0, A1, A2. There's nothing more. But you can tease out more physics from here. So let us now go back to our job of completing the problem, because there are two things we don't know in this calculation so far. We haven't quite calculated the perpendicular sensitivity, right? We don't know this. And we also haven't calculated the chi star. We don't know that either. So chi perpendicular and chi star are not known. It turns out that when you know the full problem solution, it may be possible that the answers to chi perpendicular and chi star and all these quantities are actually embedded in the solution you've already done. So in other words, what I'm saying is I am saying that these equilibrium quantities can actually sometimes be obtained from the non-equilibrium problem. How? So we'll do that. First thing I do is I know A of t, so I know A of minus I lambda because I know t goes to minus I beta. That can be done. Temperature evolution and time evolution can be mapped. So that's what I'm using. A is a function of minus I lambda. So Sxk is a function of minus I lambda. That means A0 t can be a function of lambda, A1 of t function of lambda, A2. So then chi perpendicular can be written as so A comma A, right? So then this can be written as fluctuation formula for F0 square, F1 F0 ensemble average, F2 F0 ensemble average, and then 1 over beta, this guy, that guy, that guy. So in other words, I'm basically now doing this integral on that. I'm doing the 1 over beta integral 0 to beta integral on A0 lambda, A1 lambda, and A2 lambda. Now this is the coolest thing one can think of. Why? Because you have done the dynamics problem, you actually have the ability to get new insights on the equilibrium problem that you earlier couldn't do because it was so difficult. Remember I said this was the thesis of this guy who was Fisher's student in 1967. So a significant part of his thesis was this calculation. And here we are doing it from a different angle. And we have to do these integrals. But we already know A0 t, A1 t, A2 t. So now you make it A0 lambda, A1 lambda, A2 lambda. Call it capital A0, capital A1, capital A2, and that's what we have done. And the sinusoidal functions now become hyperbolic sine. And the cosine function now becomes a hyperbolic cosine. Because in the equilibrium, what is hyperbolic cosine, the story becomes sinusoidal in dynamics. Okay, that's the mathematical structure of this problem. So, and by the way, F0 is simply a 6k. Okay, this is a, if k and n are the same, it's simply 1/4. So if there are n spins, it's n/4. Trivial. Nothing difficult here. F1, F0 translates to becoming the nearest neighbor correlation of the Ising model, which is known because it's ZZ. In fact, Tony would remember that we actually did this result in class in 519, nearest neighbor correlation of the Ising. Remember, we did that by differentiation, del jk. And then F2, F0 now becomes this new thing, which boils down to doing the second neighbor. Because you see, these two become 1/4. K becomes 1/4, and only you have this left, second neighbor. So that gives you tan squared. So nearest neighbor is tan, second neighbor tan squared, third neighbor tan cubed, fourth neighbor tan fourth. It was tan to the power r, where r is the separation. That's why you got this result. For F2, F0, which you now plug back in to our formula here. Here, F0, F0, F1, F1, F0, F2, F0. That's what we have now calculated here. We already know the A0s. We have calculated those here. So now we are ready to spell out the perpendicular susceptibility problem. So you add the pieces, this piece, the second piece, nearest neighbor, and the second neighbor piece, little bit of trick, actually quite a bit of trick, but if you go through the trick, you will get the following result. This is a famous result that was first obtained by Fisher and Burridge, this fellow who did the calculation. Okay, so Fisher and Burridge wrote a very, very large, beautiful paper with many detailed equilibrium calculations done. In our case, we managed to do that by simply going to time domain and then going the t goes to minus I lambda transform and then get here. So chi perpendicular is done. Now question is, can we get that chi star? Remember, the chi star was a difficult thing, I told you. So let me remind you what this chi star was. Yeah, here is chi star, equation 33. Chi star is not a pretty story because you have 3 spins here, and this is non-trivial. If you're going to do it using equilibrium statistical mechanics only of the Ising model, you are asking for a lot of trouble. Okay, so let us see if we can get this using our different method. And for this, I'll teach you a trick. And this trick was invented by none other than the great Kubo. It's called Kubo's second moment theorem. It's a dirty trick, Kubo's second moment theorem. So suppose you have these two vectors in your vector space, x comma y dot. Then it turns out that this x comma y dot can be written as I times beta inverse average of the commutation of x and y. Okay? It's no simple thing. Scalar product of x comma y dot can be shown, come on, as I beta inverse xy commutator with an ensemble F. So it has a potential to become really manageable. So x comma y dot is obviously x of lambda because it's the left term in the Kubo scalar product, and then Hamiltonian and y, that's what this is by definition, with i's and so on. Then you write out this part here. And then there is the, oh, come on. Stupid thing. I've not done anything. And then you have this other term here coming in. You are just breaking this term out. What did I do here? Okay, yeah. So, and then what happens is, so this is hy minus yh, hy minus, this will become yh, it will go to the other side. Again, with cyclic property of the trace, you can make it into h comma x lambda y, scalar product. And then you can essentially do this integration and show that this happens. It's non-trivial. I've given you the proof here for that reason. Non-trivial, but you can show this. So this really helps a lot as we try to calculate our chi star. So using this x to be f1 and y to be f0, so that means y dot is f1. Okay. So if you do that in equation 58, the previous equation, bang, you get this result. And it has this beautiful form in which you can place it. So this is the chi star, that complicated quantity, and it can be shown to be 1 minus 2k sinh 2k inverse. So this is like a cosec 2k and 1 plus 2k cosec of. This was one of my results that I had obtained in the thesis. It was a new result. Although Ising model at the time was already 64 years old. So anyway, this is what you end up getting in an ideal situation where all the details can be obtained. I actually don't want to go further today because I've actually covered a lot of ground, and I want you guys to be able to read through that and work through that a little bit, because I want you to do some hands-on calculations next. So in preparation for that, you'll get a feel. I won't go any further, but I want to point out something important here. When you study dynamics of many particle systems, there are essentially three groups of systems. One is you have magnetic systems, which are spin systems. And we did a simplest possible study of that. The other is you can have lattice systems, right? And lattice systems are either linear systems of harmonic oscillators, weaved together as a chain, or in 2-dimension or in 3-dimension, like a lattice solid. And the other, the third one, would be your system with electrons, and perhaps electron spins also enter the interaction, and lattice also enters the interaction. So you can have lattice, you can have electrons, and you can have spins, right? So most typical condensed matter systems of great interest today fall in the third bucket. They're lattice, spins, plus electrons. And you know the story, right? High TC superconductivity was discovered in 1986. 2026, 40 years down the road, we don't really have a solution to a high temperature superconductivity model that we can say is unequivocally the solution. Don't have that. So clearly, this third bucket you don't want to do unless you are ready for it. It's a difficult bucket, and almost everything is based upon insights and experiments, right? So we will study spin systems, and we will study lattice systems as our sort of test driving systems. We won't study that correlated system bucket, because the correlated system bucket we can study, excepting it is difficult to get results that are very helpful in terms of conclusions. So one of the systems that I want to try and tell you a little bit about, which pertains to understanding this particular push test. But for D going to infinity systems. Is basically I have a whole gauge, which is like this. So this is the XY model. And the XY model at t equal to 0 is the one that Rick, Schultz, and Mann solved. Okay? This problem is difficult. Difficult because you actually map it over to an electronic system and solve it. The non-electronic. So XY model can be mapped to non-electronic electrons. Sounds very weird, but that's how it works. Same with TI model. But I won't go to the zero temperature problem. I'll go to the high temperature problem. And in the high temperature problem, the XY model dynamics can be solved. Not rigorously with full information about all the F's, but the A0 of T can be exactly solved. So we can't really do all this fancy jazz that we have done in the Ising model because D is less than infinity, but we can do a little bit of work. Second thing I want to show you is that if you take an XY model, but suppose you cut, suppose these are the spins, and you cut a bond, then the left side doesn't interact with the right side, so this side is gone. So you get a semi-infinite model, semi-infinite. Infinite on the right, but with an edge. It's still infinite, right? It turns out, believe it or not, this spin dynamics, the edge spin dynamics here, can be exactly solved. And not only can be exactly solved, even random force can be kept. So it can be solved in its full-blown glory. And this problem I solved in 1980. It's a problem. It's very convenient. And it turns out that this magical solution tells us a great deal about memory function. Here the memory function would be sinusoidal, by the way. So there is no great glory in calculating memory function. But there is great glory because you'll actually get a D going to infinity memory function version. And it is a complicated version. So why is it solvable? Why did I solve this problem? I solved this problem because, first of all, I didn't know what I was doing when I got the solution. My postdoc advisor, who was postdoc at the time, he said, well, Shirijit, do you know how these magnetic systems behave near a boundary? So I thought about it and I said, well, I can cut a bond, I can make an edge, and then I can answer this question by calculating the spin dynamics at the edge, the spin dynamics next to the edge, next to the edge, next to the edge, going to the bottom. So I asked him, I said, should I try that problem? I mean, he was not paying me for this work. I was getting paid for some other work. He said, sure, I think that will be a fun study because I've never seen it done. So I attempted to first do the edge problem. And I couldn't believe myself that within 2 days I could solve this problem completely. I made some errors, but I fixed it up. And then I did the next spin. I couldn't solve it exactly, but I came pretty close. And then I did the third spin, and by the time I got to the third spin, I was getting bulk results. So I could tell him that if the bonds don't change much, then you get bulk within 3-4 spins. But then I realized that this edge spin solution turned out to be a very important solution because people don't know the exact solutions to these systems. And in this case, you actually solve the operator version of the Heisenberg equation of motion, which is really unbelievable. So I know of some very, very famous statistical mechanicists who are no longer alive, including one very famous Indian one, Chanchal Majumdar. I don't know if you have heard the name. Chanchal Majumdar was one of the stalwarts of the 1950s and 60s of condensed matter in India. He used to teach this model in his class because he was so impressed with it. He used to do spin models. He's passed away some years ago now, almost 30 years ago. But this head spin model I will show you, that way you'll get a good idea. And then I'll show you a few lattice studies, because one of the good things about this approach is you are not dependent upon translation invariance. Because an edge already breaks translation invariance. So if you can study models which have defects using this approach, that opens up a real landscape to explore, because condensed matter systems, solid systems with defects, are some of the most versatile and interesting and technologically worthwhile systems to probe. So good. Thanks to Tony, Vivek got to see some of this lecture. Vivek, how much of the board could you see?
Entire, I mean,
Oh, you saw the whole
the
board.
degree.
Oh, no. Okay. Good.
Yeah.
Good. Thank you. Okay. So
Yeah.
I'll close now, and we'll do the same on Thursday also. Assuming Tony is
Yes.
sicker than he is today.
I work Thursday, so.
Okay, he'll be here, he said. All right. Bye.
Yeah.
Take
Bye.
care. Bye.